Hello everyone, my name is Bhavya Gupta. I am pursuing MSc Honours Mathematics from Punjab University, Chandigarh. In this session, I will discuss about questions related to group theory which had come in past year JAM papers.
Good evening, sir. Sir, now it's fine.
Yeah, visible, no problem. Visible and audible. We can start within 1 minute. Dear friends, Maths Aspirants is an initiative by myself started in the year 2017 to help the students who prepare for competitive examinations like JAM, NET, GATE, etc. Now it is a community of not only students but also research scholars and faculty members are also there. We used to organize several online problem solving sessions to help the students who prepares for this type of competitive examinations. As a part of that series, today we have Miss Bhavya Gupta from Punjab University is with us to discuss problems from the area of group theory. She will discuss previous year questions from the JAM question papers in the topic group theory. I would like to express my thanks to Bhavya for accepting our invitation and joining with us. And also I welcome everyone to this event. Hope that the session will be really useful and fruitful to everyone. Thank you. Bhavya, welcome.
Yes, sir, I will start now. Good evening, everyone. Today, I will discuss past year JAM previous year questions which related to group theory. My name is Bhavya Gupta. Now, let's get started. First, tell me, am I audible? Everything is clear? Screen was
Yes,
visible?
ma'am.
Yes, ma'am.
Yes.
Screen is not visible.
Yeah, sure. Now it's visible?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
Yeah, thank you. And before starting, I would like to tell that if you have any doubt in any part, and if you didn't understand any answer to the question, you can ask me after finishing the question or there and then. Okay?
Okay.
Right. Now, question number 14 basically. Consider the following statements. The group Q under addition has no proper subgroup of finite index, and a group complex under multiplication C star, including 0, has no proper subgroup of finite index. And we have to tell which of the statements is true or false, right? In the options as they are given. Now, we know that Q and C star both are infinite groups, right? So we have a hint or idea kind of that they may not have any proper subgroup of a finite index. So now we prove it by contradiction. As we know, Q plus is abelian. So any subgroup of Q would be normal. And we take H to be a proper subgroup of Q. And as H is normal, so Q by H would be defined. Now, Q by H has elements of the type Q plus H. I have used plus here because our group is under addition, where Q belongs to capital Q. And we suppose that its index is finite, say n. This is the notation for index. Now, I take an element, arbitrary element in Q by H. It would be of the form R equal to Q plus H, and where Q belongs to capital Q. Now we have a result that any element raised to power, the order of the group is equal to identity, right? And R is the element of Q by H. Q modulo H, R modulo R raised to power Q modulo H should be zero element. Zero element in Q mod H is basically this. H is the identity here. So, and we are under addition, so it would be Q mod H order R equal to H. So, this was N. NR is equal to, sorry, R, yes, NR is equal to H. R is Q plus H, which is equal to H. And in cosets, we have a property that it would be directly multiplied here because Q plus H up to Q plus H n times. In cosets, we have property NQ plus H is equal to H. When this happens, like A plus H is equal to H, if and only if A belongs to H. So NQ belongs to H. What basically we have shown that R was an arbitrary element and Q is hence an arbitrary element chosen to represent R. So N capital Q would be contained in this H, and NQ is nothing but isomorphic or equal to Q because N here is basically natural number, index. Index is always a number. So hence we have shown that, which is a contradiction, because we have assumed H is a proper subgroup of Q. Contradiction happens basically kya hai? That contradiction we got is that we don't have any proper subgroup of finite index. So first statement is true. Is it clear?
Yes, ma'am.
Okay, thank you. Second part will also be on the similar lines. I can show it. Like we take a proper subgroup of C star under multiplication, and since C star under multiplication, yes, yes. Since C star under multiplication is abelian, so its subgroups would be normal, and hence C star by H will be defined. Someone's mic is on. Please switch off.
Ma'am, your mic is muted. We can't hear anything.
Bhavya,
Sorry.
your mic is muted.
Sorry.
Okay.
Where was I? We take on similar lines. We will prove this. We take a proper subgroup of C star under multiplication, and since C star under multiplication is abelian, so our C star modulo H is defined. Its elements would be of the type AH, where A belongs to C star. C star here I have denoted C minus the zero element, right? And on similar lines as we have done above, I take an element Z, ZH belonging to C star by S. This is an arbitrary element where Z belongs to C star. Now, as I have told you, order of an element raised to power, the order of element ZH raised to power, order of C star by H would be the zero element identity. Now, we have, suppose here, what we have to prove as a contradiction, index of C star modulo H index is n. So this quantity would be n. ZH, I have not taken n as addition here because group is under multiplication is equal to h. Identity in quotient group is h. What we do modulo. So from here we get that property of cosets n would be shifted here. Z raised to power n, h is h, and again by that property ah is equal to h if and only if a belongs to h. So Zn belongs to h. Z was an arbitrary element of C star, so it implies C star raised to power n is a subset of H, and C star raised to power n, where n is a natural number, is nothing but C star as a whole group. Hence, we again arrive at a contradiction because we have supposed that H is a proper subgroup of C star. Hence, second statement is also true, and we get both the statements are true and option A is correct. I hope it would be understand to you because these both the proofs were on similar lines, right? Shall I move to the next question?
Yes, ma'am.
Yes, ma'am.
Question 2. Which of one of the following statements is true? Z under addition is isomorphic to R under addition. This is clearly not true. Why? Because Z we have is countable, right? And reals, as we all know, is uncountable. So how can these two subgroups can be isomorphic? So first is absolutely false. Now for second, we can't use the same idea here because Z is also countable and Q is also countable. But we know that Z under addition is cyclic, right? And it is generated by 1 or -1. But Q under addition is not cyclic. It does not have any generator. So hence these two groups can also be not isomorphic to each other. Now let's talk about Q modulo Z under addition and Q modulo 2Z under addition, and D part is Q modulo Z under addition and Q under addition. Now for the D part, this is also not true. Why? I will show you how, because Q modulo Z under addition has every element of finite order. But Q under addition does not has any every element of finite order. For example, 1 is not of finite order. And Q over Z, how its elements are looked basically, it is under addition. So minded cosets will come under addition sign. A plus Z, where A belongs to Q, right? A belongs to Q, and rationals, how they are looked, P by Q form plus Z, where P and Q belongs to integers and Q is not equal to 0. Moreover, GCD of P and Q is 1. That is, they should be co-prime. So I have to check the order of this element, P by Q plus Z. Say its order is n, suppose. So what does it imply? That P by Q plus Z raised to power n should be equal to identity. I've told you above that identity of quotient group is Z itself, Q by Z because it is. And we are under addition, so it will come here. That is P by Q plus how many times? N times plus Z is equal to Z. Now, as we have taken that P and Q are co-prime, and this will become NPQ plus Z is equal to Z. Property of cosets again, NPQ belongs to integers if and only if. Now we know that P and Q are co-prime, so Q doesn't divide P, but Q should divide N. So order, what is basically order of an element? Smallest positive integer such that e raised to power n is equal to identity. This should be smallest. And here smallest would be Q itself. Hence we get order of P, Q plus Z is Q, where these P and Q are co-prime. For example, take 2 by 3 plus Z. What will be its order? If we will do it 2 times, plus 2 by 3 plus Z, it would be 2 plus 2, 4. 4 by 3 modulo Z, when we will do, it would be 1 by 3 plus Z. Hence we haven't got integers, which is the identity of the group. Hence we have to do it one more time. 2 by 3 plus Z 3 times, that would be 1 by 3 plus 2 by 3, which is 1 plus Z, and 1 belongs to integers, so it is integer, and hence we get order is 3. And what I have proved above, this was just an illustration because they are co-prime and Q is 3 here, hence its order is 3. In fact, it's every element is of this type, and I have showed every element is of finite order. Now for our C part, that obviously I have showed that rest three options are incorrect, so obviously Q by Z under plus would be isomorphic to Q modulo 2Z under addition. But in case if we want to prove it, we can show it by a mapping. That is phi from Q modulo Z to Q modulo 2Z, taking phi x plus Z, where x is a rational number, equal to x plus 2Z. You can easily prove that this is an isomorphism. As homomorphism, we need to show x plus Z plus y plus Z is equal to phi x plus y plus Z, which in turn is equal to phi x plus y plus Z, which is equal to x plus y plus 2Z, which is equal to x plus 2Z plus y plus 2Z. Hence phi of x plus z plus phi of y plus z. Onto is clear because if you take any element here, x is already lying here, and you can show that this map is onto. For 1,1s, say x plus z belongs to kernel of phi, which implies kernel of all those elements which are mapped to identity of this, and its identity is 2z. So phi of x plus z should be 2z, that is x plus 2z is equal to 2z, and by property of cosets it implies x belongs to 2z. And hence, as 2z is a subset of integers, it implies x belongs to z, and z was the identity in the group Q by z. So x plus z would be of the form z itself, that is kernel contains only one element, that is identity. Because I have shown that x belongs to integers, so x plus z would be z. Hence we have proved a map is isomorphism, and hence the groups are isomorphic. But in paper it is generally suggested that it is better if we can do by crossing the options, because that was much easier and we have done it in an earlier time. It's understood?
Yes, ma'am.
Another question. Let G be an element of S7. S7 is symmetric group permuting 7 elements such that G commutes with the element 2647. Now, we have that conjugacy class of a sigma or any element is order of is equal to the index of Sn over, this is centralizer of sigma. What is centralizer basically? Centralizer contains all those elements tau belonging to Sn such that tau and sigma commutes. Tau sigma is equal to sigma tau. And conjugacy class of sigma contains all those elements which are similar. That is basically or conjugate to each other. Sigma is conjugate to tau if there exists eta belonging to Sn such that tau is equal to eta inverse sigma eta. This you can generalize also if for any element A belonging to a group G. Then also this holds. Now, as we have to show number of elements which commutes with this. Basically, we need this, we need to find centralizer of this sigma. But we know conjugate, how to calculate its conjugates, as we have a property, a theorem. Sigma is conjugate to tau if and only in Sn, if and only if they have same cycle structure. And one more formula I would like to tell you, that is number of permutations of the type. This is a cycle of length L1, and this is also a cycle of length L1 up to N1 times, and another cycle of length L2 up to N2 times, and so on up to a fixed number, say T. Then number of permutations of such type which have same cycle structure like this would be n factorial divided by products T I is equal to 1, n I factorial product Li raised to power ni. So here we had element 2643, 4 cycle structure, and we are in S7. So basically we need to find 1, 2, 3, 4, and we have to complete it till n. In above formula also, it is here only sum of all these individual elements is n. That is n1 plus n2 up to nt should be n. It is prerequisite to apply this formula. Otherwise, it will give wrong result. So here also we need it. We have 1 cycles, 3 1 cycles, and it will complete our counting 1, 2, 3, 4, 5, 6, 7. So now we can apply this formula. 7 factorial by 1 cycle of 4 length, 3 cycles of 1 length. This was length. 1 raised to power 3, 1 factorial, 3 factorial. Now don't calculate it. Why? Because in the question what we have asked was this. This we were asked, and we have calculated this. Calculate this, it would be order of Sn, right? And we have to calculate this. Sn order is n factorial, as we all know. And here we are getting the same type. This is order of conjugacy class of sigma, and we require this centralizer of sigma, all those elements which commute with sigma. So just calculate this. That is 4 into 3 into 2. 6 4s are 24. Answer is 24. I'm again telling you, don't make the mistake of using this formula without taking into the consideration these 3 cycle types. Or we have a less complicated formula for single cycles, not single cycles, a cycle. Number of cycles of length 4 in S7 would be 7 into 6, because we have 7 choices here, 6 choices here, 5 choices here, 4 choices here, and this is 4 cycle, and a cycle can be represented by 4 methods. So 4. But I won't suggest you to apply this formula. 7, 6, 5 into 4. 4 factorial. I won't suggest you to apply this formula because here you have to 4 here. Here it will become 4 because here you have to convert it into 7 factorial above. That's why. Otherwise, it is also easy formula and you can apply. It will also give same result, that is 24. 24 elements commute with sigma. Another question. Consider the following group under matrix multiplication H. Its elements are of the type upper triangular matrix, basically 1 1, not upper triangular, subset of upper triangular matrix 1 1 1 0 0 0 PQR, and we have to tell whether its center of the group is isomorphic to what. Now, what is center of a group is equal to X belonging to G, all those elements of G, which commutes with all the elements of G. That is, XY is equal to YX for all Y belonging to G. So, let's suppose 1 1 1 0 0 0 PQR. It's adjustable now. Belongs to H. And we have to calculate elements of its center. Suppose it is center of H. So 1 1 1 PQR 0 0 0 1 1 1 ABC 0 0 0 is equal to 1 1 1. By the property I just told you about the center, 1 1 1 0 0 0 PQR, where this element is an arbitrary element of H. So for this to be in center, this property should hold. We will now matrix multiply them, which would give us the result 1 plus 0 plus 0 P plus A 1 0 B plus CP. I'm assuming that you know matrix multiplication, otherwise we just have to this first column of this is multiplied by 1 1 1 0 0 0 0 0 0 and we add them. Then this column AAA 1 1 1 0 0 0, then add them. So here was it A and I kept it A. Here it was 1 1, so P 1, and in the next it was 0, so 0 0 0 came here 0 and no other terms came. B plus CP plus Q, C plus R 0, and here also do matrix multiplication, which would be 1 1 1 0 0 0 P plus A C plus R. Now here B and Q would remain B plus Q plus AR. So for these two matrices to be equal, or individual entries must be equal, P plus A is equal to P plus A, because
I think
yes sir,
in first matrix the last option, the last entry is 1, right?
yes sir,
A33.
by mistake. Last entry is 1. In individual entries should be equal. P plus A is equal to A plus P or P plus A, because in reals addition is commutative. In similar, C plus R is equal to C plus R, but here we need them to be equal. B plus CP plus Q is equal to B plus AR plus Q, if and only if B and Q will get cancelled. We are in reals because CP is equal to AR. Now, mind it that we have taken A, B, C, it was an arbitrary element of H, because the condition should be hold for all the elements belonging to H. So A, B and C are arbitrary elements in reals. They are arbitrary, so this condition to get satisfied, we need to have P is equal to 0 and R is equal to 0. This condition is because these were arbitrary. They can be any real. That's why for any real, this condition to hold, we need to have P equal to 0, which would imply R equal to 0. So we now have how the center of H would look like. Center of H would look like 1 1 1 0 0 0 0 here, 0 here, and an arbitrary element here. Q belonging to reals. Now look back at the options. Here it was isomorphic to R square. Here also it was coming 2 times R. But we only have one element varying here. So C and D options cannot be true. But here now we have that which option to take, because here also they are talking about single R and here also reals. And it is not that if our group is under matrix multiplication, so center would also be isomorphic to multiplication. Don't think like this. It may be isomorphic to reals under addition. And moreover, we will show a bijection, isomorphism from center to reals under addition. Now, phi from Z to R under addition .
Hello. Hello.
Yes, sir.
I think your voice is not coming by at that time.
Now it's
Okay.
coming.
Yeah, it's okay now.
Uh,
But your presentation is turned off.
my
Presentation screen.
screen is not coming now.
Yeah.
Now it's coming.
No, it's not coming now.
It's not there. You have to restart, I think. Okay, now it's okay. Now it's okay. Yes.
It happened automatically.
Okay, no
I
problem.
didn't do
No
anything.
problem. No problem. Okay. Continue.
So now I was on that I need not prove 1, 1 and on 2. It is very clear from the map I have defined. I must prove homomorphism, that is phi of x, y. I have taken here dot product because ZH is a subgroup of group under multiplication, so it would be also under multiplication, is equal to phi of x plus phi of y. I have taken plus here because this was under addition. We have to show this. I have taken an x element, suppose with q, 1 0 0 0 1 0 1 0 q plus, multiplication 1 1 1 0 0 0 0 0 p. When we will multiply these matrices, we will get 1 1 1 0 0 0 0 here, basically 0 0 p plus q, right? So it would be p plus q by the way I have defined our map. Now p plus q is phi of 1 0 0 0 1 1 0 0 p plus phi of 1 0 0 0 1 0 p q. And hence I have shown this. Don't worry about that here q was coming first and p was coming afterwards, because in real gender addition is commutative, so I can take this here also and this here also. So it would be a homomorphism. Homomorphism 1 1 onto, and hence an isomorphism implies our center of H is isomorphic to R under addition. Is it clear?
Yes.
Now another question. F is such that omega belongs to complex omega raised to our 2020 is equal to 1, 2020. This is 20th roots of unity, because we define nth root of unity as omega raised to power n equal to 1. So this is basically this set, 20th roots of unity set. Now we are considering a group G and H. G has elements of the form omega, Z, 0, 1, and where omega is coming from F. Z is a complex number. 1, 1 and Z here under matrix multiplication. Then number of cosets of H in G. Now, what are basically number of cosets of H in G? That is index of H in G. Its notation is G by H. So to find its number, I can also think of an idea to define a map such that its kernel is H, because I am seeing here that H is a subset of G. Clearly, because here it is 1, and naturally 1 belongs to this F. Omega raised to our 2020 is 1, so 1 belongs to it. So if I consider a map phi from G to F, it is a very simple map. Sorry, G to F. Because in options what I am seeing is 2019, 2020, infinite, or 10, 10. So it may be that number of cosets is related to this group F. And F has how many elements? 2020. Nth root of unity with which it forms a group has n order only. So a map phi from G to F such that how our elements of G were omega, Z, 0, 1. Now I have to map to an element of F, and we have an element of F in G, that is omega. So it is a well-defined map, and moreover it's onto also. But yes, it's onto. We need to show it. It's onto because if I take any arbitrary element omega in F, there exists omega Z 0, 1 belonging to G such that its map is omega. So it is onto. Now phi is homomorphism also. Phi, I am taking two elements omega 1 0 z1 1 omega 2 z2 0 1. When we will multiply these two matrices, we will get omega 2 2 2 0 0 0 omega 1 omega 2 0. We are only considered with this element. I need not calculate these because we are just mapping this element. So it is omega 1 omega 2, which is equal to phi of omega 1 0 z 1 into phi of omega 2 z1 z2 0 1. It is a homomorphism. So we have fundamental theorem of homomorphism. What it says basically, if phi from G to G dash is a homomorphism, then we have G by kernel of phi is isomorphic to a subgroup of G dash. We have shown that it is onto. So when it is onto, it is isomorphic to G dash itself because phi of G is equal to G dash. That's why. Now we have just one little thing left, that is we have calculated its kernel. And kernel, to find kernel, it's very easy. As we can see, if we take an element omega z 0 1 in kernel of phi, then its map should be identity. And what is identity in F? F is the nth group of nth roots of unity. It is under multiplication. So its identity is 1, which implies omega is 1. So what we have got in kernel of phi? All those elements in which omega is 1. That is exactly H itself. What we have got in kernel. Kernel of phi is H here. And we have got that G by kernel of phi, that is G by H, is isomorphic to F. Here our G dash is F. And their orders will be same. Order of F is equal to order of G by H. Moreover, this only we need to show because number of cosets is G, index H, which is equal to this. Order of F was 2020 because it is nth root of unity, 20th roots of unity. Hence our answer is 2020. It cannot be infinite, it cannot be 2019 because we have calculated an exact number. 2020 is the number of cosets of H and G. Now, next question. Let phi from S3 to S1 be a non-trivial injective group homomorphism. Then number of elements in kernel of phi. We are not specified here what is S1 here. But still we need not worry. This question is very easy. How? We have given two options, non-trivial, non-injective, and S3. S3 is symmetric group, permuting three elements, 1, 2, 3. S3, normal subgroups of S3 are 0, A3, and S3 itself. And for a group homomorphism, what we require is phi. What we require is kernel of phi, because every group homomorphism links itself to the kernel. Or even if we can assume phi to be a non-injective group homomorphism, non-trivial, from S3 to S1, and we have to find number of elements in the kernel. What can be its kernel? Kernel have three choices because kernel is the normal subgroup. 0, A3, S3. It should be non-trivial. That is, it should not be a zero homomorphism. When we get zero homomorphism, 1 second. When we get basically a zero homomorphism, when its kernel is S3, all the elements are mapped to 0. So this cannot be the case here. And non-injective. Phi is 1, 1 if and only if kernel of phi is identity. Here identity will come not 0, 1, because in S3 we have identity 1. Identity, you can take it as an identity. So neither kernel of phi can be 1 identity, because it will give us injective group homomorphism. So we have left with only one choice, that is A3. A3 would be its kernel, and number of elements in kernel would be the order. Order of A3, as we all know, is order of S3 divided by 2. Order of A3 is equal to order of S3 is 3 factorial by 2. Factorial formula 3 into 2 into 1 by 2, that is 3. So our answer is 3. Is it clear?
Yes, ma'am.
Suppose that G is a group of order 57 which is not cyclic. If G contains a unique subgroup H of order 19, then for any G not belonging to H, what would be the order of G? We are given that it is not cyclic. We are given that H is of order 19. G 57, factorization of 57 is 3 into 19. Order of H is 19. Any element which is contained in H, as we know, order of an element divides order of the group. So order of G divides order of H, that is 19. 19 is prime, so we have only two choices left, that is order of G can be either 1 or 19. Now, how many elements do we have of order 1 in H? That would be just identity. And how many elements of order 19 we have in H? Now, we know that any group of prime order is cyclic and hence isomorphic to Zn. Right. So how many elements of order 19 do we have in Zn? That is phi of 19. Phi is Euler's phi function, which is phi mn, where m and n are relatively co-prime, is equal to phi of m into phi of n, and phi of n1 raised to power k1, n2 raised to power k2, p, up to pt raised to power kt is equal to p1 k1 minus P1 K1 minus 1 into P1 K2 minus P2 K2 minus 1 and so on till this. So here we have it is a prime, so its value would be 18. Its value is 18 here, 18 elements. Oh, we just need to calculate the order of G. So we are left with only order 9. Sorry, I took extra time. Because any element of G, dividing order of G would have 4 choices, 1, 3, 19, 57. 19 is in the H, 1 is in H. 57, if we have any element of order 57, it would make the group silent. So 57 is also left out and we are only left with 3. This was a much easier question. I took extra time. And hence our answer is 3. Let H and K be subgroups of Z144. If order of H is 24, order of K is 36, then order of subgroup H intersection K is. Now we have a formula that order of HK is equal to order of H into order of K divided by order of H intersection K. Moreover, Z144 is abelian. So H and K would be normal subgroups of G and therefore HK would be a subgroup of G. Here G is Z144. And H intersection K order divides order of H and order of K. Why? By Lagrange's theorem, because H intersection K is contained in H and K both, therefore it would be a subgroup of H and subgroup of K. What does Lagrange's theorem says? That order of the subgroup divides order of group. So that is H intersection K divides order of H and order of K. It would divide GCD of order of H, that is 24, and 36. Its GCD is 12. So we can have all the 4 choices here. But with this formula and that HK is a subgroup of G, we can see that if we take H intersection K to be 3, then order of HK would be 24 into 36 into 3. It would be greater than 144. As you can see, 144 is 12 into 12. I would cut here by, it would come 12. Here we have 2. So it cannot be 3. And if we have 4, then it would be 6. 6 is the 6 is the 18, 2 and 6. This is also greater than 144. So we cannot have as an option 4 also. We are left with 6 and 12. 12 into 12 by 6, 12 into, 24 into 36, 24 into 36 by 12. It would come out to be 48 and it would come out to be, by 2 I am cancelling, 12, 12, 12. It is 144. 144 is possible. So we can have 6 also and 12 also. Both the options are correct. H intersection K, we are not getting any contradiction here. So this can also be possible where H and K will give the whole subgroup Z144. Another question. Let G be a non-cyclic group of order 4. It is non-cyclic. We know that order 4 groups are only Kleins 4 group and Z4. But even if we don't know this fact, we can solve this question. We consider the two statements. There is no 1-1 homomorphism from G to Z8. There is no on-to homomorphism from Z8 to G. We'll suppose there exists phi from G to Z8, 1-1 homomorphism. I told you about the fundamental theorem of homomorphism. That is, if we have phi from G to G dash, a homomorphism, then we have G by kernel of phi is isomorphic to phi of G, which is a subgroup of G dash. And if we are given phi is onto, then G by kernel of phi is isomorphic to G dash itself. And if phi is 1-1, we know kernel of phi is identity. We will use these three facts here. So if it's 1-1 homomorphism, then we will have that G by kernel of phi is contained in Z8. That is basically a subgroup of Z8. So Z8 is cyclic, but we are given G to be a non-cyclic. If G is non-cyclic and G by kernel phi is a subgroup of G, so it would also be non-cyclic or non-abelian. How can it be isomorphic to a subgroup of Z8? Because in Z8, every subgroup is cyclic and abelian. Hence, there exists no injective 1-1 homomorphism from G to Z8, which is a true statement. And in third, let phi from Z8 to G be an onto homomorphism, which will imply Z8 by kernel of phi is homomorphic to G. Z8 is cyclic, it's every subgroup. This is also a subgroup of Z8, it would be also cyclic. But G is given to be non-cyclic, so it can also be not possible. And hence, this statement is also true. But we have only, hence C is true and A is true. Now, next question. Let G be a non-abelian group. Y belongs to G. And let maps F, G, H from G to itself be defined by Fx is equal to Yx, Y inverse, Gx is equal to X inverse, H is equal to G of G. And we have to tell which of them are homomorphisms. We are given here that G is non-abelian group. Now, what is a homomorphism basically? It should satisfy a property. Phi of xy is equal to phi of x into phi of y. This property we need to check in which it is holding. Now, h is g of g. H of x is equal to g of x. This is equal to g of x inverse, which is equal to x inverse g, operation of g is x inverse, inverse. Inverse of inverse will give us h. H is nothing but identity map. An identity map is always a homomorphism. So in the options where H is not given homomorphism, we should cut them, but here is no such option. Now let's check of G and F. G of xy is equal to x by inverse. Now we will use reversal law or shocks and shoes property, that is, it would be y inverse, x inverse. Why it is known as socks and shoes property? Because first we wear socks, then we wear shoes, but when we have to take them out, we remove first shoes, then socks. Just a way to memorize this formula. But we are given that G is non-abelian. So it would not be equal to G of x into G of y, which is x inverse, y inverse. Hence G is not a homomorphism because we are given G is non-abelian. G is not a homomorphism, G is not a homomorphism. D option is incorrect, A option is incorrect. Now we only have to check for F, whether F is a homomorphism or not. F of xy, I won't take here y because y here we are using here, it is a particular element. I will consider x1, x2 equal to y, x1, x2, y inverse, y, x1. Here I am doing y inverse, which I can do because y inverse is nothing but identity. And we know the property of identity, whenever it is multiplied, it leaves the operation unchanged or the elements unchanged. So x2, y inverse, combine this and combine this, it would be f of x1 and f of x2. Hence, it is a homomorphism. So, in this, we have B option also correct because H was also a homomorphism and G is not a homomorphism, and F is also a homomorphism and G is not a homomorphism. Now, is it clear?
Yes, ma'am.
Thank you. So now another question. Let x be a 100 cycle. 1 to 3 up to 100. And y be a transposition. Transposition is basically a 2 cycle, 49, 50. In this permutation group. And we have to calculate the order of xy. Now, everyone know the formula that if we have to calculate the order of xy, it would be LCM of order of x, order of y. But this formula should be used only when x and y are disjoint. Here they are not disjoint, so don't use this formula and write that its order is 100. It's wrong. Okay? So we have to now compute xy basically. 1, 2, 3 up to 100 into 49, 50. There are two ways to do it. First, directly compute this, or first see how a smaller example works and then come to this. For example, if I take a 4 cycle in S4, that will be 1, 2, 3, 4, and do it with 2, 3. They have also taken the middle elements. So here 1 goes to 1, here 1 goes to 2, 2 goes to 3 here, and 3 here goes to 4. 4 here goes to 4 itself, so 4 goes to 1, and cycle is complete. 3 goes to 2, 2 goes to 3, 3 is complete. So we get a 3 cycle, 1 to 4, and there is no trace of 3. Why? Because this 3 is just nothing. We can write it at 1 to 4. So its order is 3, not 4 or 2. I hope you know how to do the operation in SN. Is it clear?
Yes, ma'am, it's clear.
So similarly in this, 1 goes to 1, 1 goes to 2, 2, 2 goes to 3, and we can go up to 48. Here 48, 48 goes to 49. Now here 49 goes to 50 and 50 goes to
49.
50 goes to 51. 50 goes to 49 goes to 50 and then we will come here. 50 goes to 51. Clear?
Yes, ma'am.
Right. So we will now same sequence will go on. 51 goes to 51. Here 51 goes to 52 up to 100. Now what we have observed here is there is no element of 50 here. One element less. That is, it is a 99 cycle. 99 cycle. What is the order of 99 cycle? That is 99 itself. Because order of n cycle is n. Hence, we have got order of xy is 99. Here also it was one less. On a similar observation, we could also write, but computing is also easy. It is not a difficult task here. It was just a transposition. So answer is 99. Now, G be a group satisfying the property that F from G to Z21 is a homomorphism implies Fg is 0 for all G belonging to G. Basically, if we take any homomorphism, it would be a 0 homomorphism only. That is, from G to Z21, we only have 0 homomorphism. No other homomorphism. That is only 1. And these in the options which we are given are all the Zn form. And we have a formula that number of homomorphisms phi from Zn to Zm are GCD of n and m. Here what we require, in the question it is given, there we have only one homomorphism. So GCD should be with 221 should be 1, which all elements have GCD 1 with them. First we do the factorization of 221. That would be 13 into 17. 21 can be, because 21 and 2 to 1, no factorization is coming, it is 3 into 7. 51, 17 is coming, 17 into 3, so it cannot be. 91. 91 is also 7 into 13. 13 7 is a 13 is coming, so this cannot be. Well, its GCD would be 13, not 1. And in 119, we have 7 into 17, so this can also be not possible. Hence, 21 is the only correct option. Now, another question. It was clear? Was it clear?
Yes, ma'am. It was clear.
Yeah. Another question. H be a quotient group QZ. I've already discussed this group in the first question, I guess. QZ, consider the following statements. Every cyclic subgroup of H is finite. Every finite cycle group is isomorphic to a subgroup of H. Second statement is a bit strong statement. Let's first check first statement. Now, it is also an example of a group, infinite group, in which every element is of finite order. How its elements are basically P by Q form plus Z, where P by Q belongs to rationals. P and Q are co-prime, Q not equal to 0. Now, every cyclic group, subgroup of H is finite. Let G be any cyclic subgroup of H, which would imply G is generated by some element of H. Say A, where A belongs to H. Order of G is equal to order of A in cyclic group. Order is equal to the order of the element, that is its generator, which is finite. And we know every finite cyclic group is isomorphic to Zn. So G is isomorphic to Zn. G is a subgroup of H, and hence we have shown that every cyclic subgroup of H is finite. Finite we have only shown by this, that every element in Q by Z is of finite order, and order of G is equal to order of A, which is finite, and hence every cyclic subgroup of H is finite. Now for second statement, every finite cyclic group is isomorphic to a subgroup of H. I have used this. Every finite cyclic group is isomorphic to Zn, and we have to show that Zn is a subgroup of H. For that, what I will do is, I have told you earlier that P by Q plus Z has order Q if they are co-prime. We can construct an easier example to have an element of order n. That is, if we have to show finite order G is n, then 1 by n plus Z order would be n, because 1 and n are co-prime, so its order would be n, and it is an element in H. So subgroup generated by this will be cyclic and of order n, so it would be isomorphic to Zn, and it is a subgroup of H. So by first and second statement, we have got that G isomorphic to 1 by n plus Z is a subgroup of H. And hence our second statement is also true, because I have shown a cyclic group isomorphic to a subgroup of H. One is true, both are true. Consider a group Z square, A plus A comma B, AB belongs to integers under component wise addition. Then which of the following is a subgroup of Z square? What is the property of subgroup? That we say H is a subgroup of G if H is non-empty and AB inverse belongs to H for all A and B belonging to H. Or we can divide this one property into two, that is AB belongs to H for all AB belongs to H, and A inverse belongs to H for all A belongs to H. Now, in this group Z square is equal to A comma B, AB belongs to integers under component wise addition. We have the following subgroups. AB is equal to 0. Now this is not a subgroup, as we can see. It is under component wise addition. So I have a counterexample for this. Basic two elements 1 comma 0 belongs to this subgroup H, because 1 into 0 is 0, plus 0 comma 1. This also belongs to this subgroup H, because 0 into 1 is 0. Do it component wise addition, that is 1 plus 0 comma 0 plus 1, which would be 1 into 1. But this does not belong to H, so it is not closed under addition. It is not a subgroup. Now, in this, first check that whether every subgroup has the identity element. And in Z square, what identity element we have? That is 0, 0. Because 0 is the identity of Z under addition. So, but this, if we take 3 into 0 plus 2 into 0, it would be 0, not equal to 15. So, it does not contain identity. So, cross out this option. We are left with C and D. Now, this also, there is a flaw. We can find a counterexample basically. What I mean is 1 comma 7, as I have done simple example. Here 7 divides 1 into 7 plus 7, comma 1. Add them component wise. 1 plus 7 is 8. 7 plus 1 is 8. But here 7 doesn't divides 8 plus 8. Hence D is the only correct option. Moreover, we can prove it also as AB inverse belongs to H. We have to prove. We know that a 0 element belongs to this group because 2 divides 0 and 3 divides 0 is trivial, so H is non-empty. I have to show this property. AB inverse in addition means A minus B. I have to show. I have to take two elements A and B here. I take it A1, B1 and A2, B2 belongs to H. Then it would imply 2 divides A1, 3 divides B1 by the definition of subgroup. 2 divides A2, 3 divides B2. And what I have to show is A1, B1 minus A2, B2 is equal to A1 minus A2, B1 minus B2. Now I have to show that this element is divided by 2 and this element is also divisible by 3. Now by this and this, I have, this is a simple number theory property that if 2 divides A1, 2 divides A2, then it is 2 divides their difference also. Similarly, this and this will imply 3 divides B1 minus B2. And hence we have that this element belongs to H. XY inverse belongs to H. If I take this element to be X and this Y, and hence it is a subgroup. Proved. Another question. Suppose F, G, H are permutations of the set alpha, beta, gamma, delta. We have only 4 elements in this set. F interchanges alpha, beta, but fixes gamma, delta. So how F will look like? Alpha and beta are interchanged. Alpha goes to beta and beta goes to alpha. But fixes gamma and delta. Basically, it does not touches gamma nor delta. So we will not include it in F permutation. And G permutation is such that it interchanges beta, gamma and fixes alpha. Here it is alpha. Alpha delta. H interchanges gamma delta. Right? Now we have to find permutation which interchanges alpha and delta but fixes beta and gamma. Now we have to compute all these mappings because there is no other way. F of G of H of G of F is equal to alpha beta, beta gamma, H is gamma delta, G beta gamma, F is alpha beta. Now alpha goes to beta, beta goes to gamma, gamma goes to delta, delta, delta. Now delta goes to gamma, gamma goes to beta, beta goes to alpha. Closed. Now check for gamma. gamma goes to beta, beta goes to gamma, closed. Beta goes to alpha, alpha goes to beta, closed. So it is alpha delta, hence A is in our option. G of H of F of H of G. G beta gamma, H is gamma delta, F is alpha beta, H again is gamma delta, and G is beta gamma. Here you can see that these two permutations are disjoint, and we have a result that disjoint permutations commute. So we can here do it alpha beta and gamma delta, gamma delta. Here these are also there. Gamma delta into gamma delta would give us identity. Why? Because transposition is of order 2. AB into AB will give us identity. You can check it also. So we are just left with beta gamma, alpha beta, beta gamma. Here they are not disjoint, so we cannot convert. Beta goes to gamma, gamma goes to beta, beta is closed. Alpha, alpha goes to beta, beta goes to gamma. Hence, in this it does not interchanges alpha delta as alpha is going to gamma. So this option will not complete. Even if we want to complete this cycle, it would be gamma goes to beta, beta goes to alpha, which is closed, and here is no delta, so no delta will come. Now another.
Yeah,
Yes.
our time is almost, so we have to finish by the coming problem. You can do
Or
that,
sir,
the next one. Okay.
next are easy problems only. I think
Okay.
I can do it in 7 minutes.
Okay, no problem. We need some time for interaction as well. That is fine. Okay.
In this, you can check D will also be in our option in this similar manner. Now I will move on to the next question. That is basically order of an element 1, 2, 3, 2, 4, 5, 4, 5, 6 in the group S6. Mind it, we cannot use the formula of LCM here also because they are not disjoint. Compute these elements 2, 4, 5, 4, 5, 6. It will come out to be, due to shortage of time, I'm not telling proper how computation, because in earlier questions also I have told it many times how computations are done. So I'm doing it directly. 4, 3, 1, 2 and 5, 6. Now you can take an LCM. That is LCM order is 4. Its order is 2 and LCM will come out to be 4. Hence order of element is 4. A6 be the group of even permutations of 6 distinct symbols, even. Number of elements of order 6 in A6. Number of elements of order 6 in SN. S6 basically. What are they? 6 cycle and one more is there. 2 cycle and a 3 cycle. It is of order 2, it is of order 3 and LCM would be 6. Disjoint. Obviously, we can have a disjoint 1, 2, 3, 4, 5. 5 symbols. Here there are 6 symbols. But this 6 cycle is odd because it will result in odd permutations as 1, 2, 3, 4, 5, 6 will give us 1, 6, 1, 5, 1, 4, 1, 3, 1, 2. These are odd number of transpositions. It is just a method to convert a cycle into product of transpositions. Here you can even take arbitrary elements A1, A2, A3, A4, A5, A6, A1, A6, A1, A5. It will come out to be odd. And here also this 3 cycle would give us 2 transpositions, and we have already 1 transposition. So in total, we will have 3 transpositions. So this is also odd. And hence we have no element of order 6 in A6. Because we have only 2 choices, and these both 2 choices give us odd permutations, and it would be 0. Thank you everyone, because
I
next.
would like to thank Bhavya for presenting a variety of problems from group theory. Yeah, not only multiple choice type, multi-select type, and also numerical answer type questions also were covered.
Yes, sir.
And if there are more questions, we can have one more session in nearby future if possible. We can think about it. Now it is the time for interaction. Now, students, you can express your comments or ask your doubts, because you know Bhavya is just your senior, so you can consider her as your Didi and you can ask her for study tips.
I'm
Bhavya,
pursuing.
please, yeah, Bhavya, please stop your presentation. That will be more better. Yeah, of course, we will share the notes in our groups. Someone is asking me about.
We will also
We will
share the recorded video. So
yeah, yes. Okay, please, all of you are requested to interact before
evening,
starting
ma'am.
interaction. Yeah,
good
yes.
evening.
Good evening, ma'am. My name is Meera. I'm from Calicut St. Joseph College, Devgiri. I'm a fifth semester student of BSc Mathematics. Today's class was really a nice experience for me. As a person, I felt difficulty in solving the jam paper, the group theory part in the jam paper. But today, the class provided me with different ways of solving a problem. You gave more than one way to solve a question, and you give each and every definition for the steps you took up, and it was really a helpful class for me, and I heartily thank you for your classes, and I'm looking forward for more classes from you. Thank you,
Sure.
ma'am. Thank you so much.
Thank you, Meera.
Yeah, if you have any other tips also, because I am pursuing MSc Honors Mathematics from Punjab University, Chandigarh. If you want to discuss anything about study also, or which book to refer, anything you can ask. And even for the session also, you can tell if anyone is interested.
Yes. Others? Yes, Amrita. You can keep your video. Yes.
Is it seen right now? Ma'am, my name is Amrita. I'm from St. Joseph's College, Devagiri. Ma'am, your class was really nice, and all the questions you discussed were of high standard questions. We used to see so many questions which were literally simple, but when these questions were of high standard, and it was it was a bit difficult to understand. Also, not to understand, just to know how the question is or how to solve it. So it was really good, ma'am. Okay, ma'am.
Amrita. Thank you. Okay, others?
Hi, ma'am. My name is Kavya. I'm from Mathematics Mitra. It was really nice class which you have taken, and you have solved many problems through variety of ways. Thank you for being with us. Thank you so much.
I hope my English was clear and I haven't used any Hindi word.
Everything is perfectly okay, Bhavya, but you know, as Amrita pointed out, the questions are a little bit of higher standard compared with the students of BSc, because they have just studied the basics of group theory. So I think there may be some little bit of difficulty for understanding the things for them. But anyway, they have to understand these things, because you know all these problems are
But
taken from previous year JAM question papers.
yeah, I haven't as such selected difficult questions. I have just taken these questions are from JAM 2020, JAM 2019, 2018, up to 2011.
Yeah, the things are right from your side, but you know, these people are attended the classes via online mode and all that. There are many difficulties they faced due to all this pandemic and all that.
Right, sir, I can
So,
understand.
yeah, but anyway, they have to overcome all that issues, because you know, JAM examination is very near. It's going to happen on the coming February.
14 February.
Yeah. Okay, others.
Hello, ma'am.
Hello.
My name is Satira. I'm also a third year BSc student from Kerala. Ma'am, your class was very informative. I got to know about a good set of questions, and your way of approaching them was also very good. Thank you, ma'am, for the class, and expect many more classes from you.
Thank you. Thank you. It's a very good compliment.
Yes, thank you, Adira. Others?
Hi ma'am, I'm Gopika from
Hello.
Delhi University.
Yes.
Yeah,
So,
yes, go ahead.
yeah, as everyone told, it was very nice problem solving session, brainstorming problem solving session, and thank you for spending this time. So, in between, my charge was lost and I missed a little bit. So, I'm hoping to follow it in the recorded class.
Yes,
So,
yes.
thank you so much, ma'am.
Welcome.
Yeah, thank
Okay, thank you, Gopika. Yes, Vaishnavi, you can. Vaishnavi, I think you are muted. Your voice is not coming.
Voice is cutting.
Vaishnavi, is your audio device okay? It's not audible from your side. Okay, others? So feel free to express your comments.
Vaishnavi has joined.
Yeah. Vaishnavi?
Sir, is it audible now?
Yes.
Yeah, it's audible now, but you are not visible now.
I just switched off the video.
Okay.
Ma'am, it was a nice class. For me, the topics under the group theory is more difficult for me. And you have discussed many jam problems. Only you have discussed only the jam problems, and some of the questions were I practiced already. So I was able to follow some questions, but I was not able to follow some other questions because it was already told that it was some more high standard questions. So can you suggest me some tips? How can I can become more strong in my concepts in group theory, and also while it comes to the applying section, and also can you suggest any tips for that?
Book basically.
Not books. The way how can I approach to all those things, all the concepts or that problems?
Right. Now, first, when you understand a topic in a group theory, suppose you're understanding normal subgroups also, you should understand that from where normal subgroups are coming and what is its definition and its examples. Because from examples also we get many information which can be applied in questions also. Like in lecture also I have told about Q by Z group. It is an infinite subgroup with all the elements of finite order. And we have more such examples like Z by NZ. You have studied normal subgroups?
No, ma'am, we haven't
Yeah.
reached that.
Okay. You are just basics of groups and subgroups.
Yes, ma'am. I have only basics, groups and permutation groups till that.
Oh, okay.
Bhavya, it is there in their syllabus, but their classes were not reached up to that, I think.
Yeah, because if they have studied permutations group, they should have studied normal also. The thing is, you should understand the concept clearly. Then you should try to solve the questions which are given in the book exercises by yourself without seeking the help of internet. Because all the solutions are available in internet, and many people use internet to solve the questions. You just don't see internet to solve questions, and your grasp will be good until unless you cannot solve that question. Then you can take help of internet or a teacher or your classmate. This is a good
Okay,
approach.
ma'am. Thank you, ma'am.
Yes, thank you.
And
Yeah, thank you,
also we
Vaishnavi.
expect more classes from you.
Thank you.
Okay, others.
Hello.
Hello.
Hello, ma'am. Myself Lakshmi. I am also a third year BSc student from Kerala. Ma'am, your class was really good, and that problems which we studied with the basic group theory in our college now, in our fifth semester. And these problems really helped me to go somewhat deep into that concept, that basic concepts like normal subgroups and that permutation groups and all. Thank you so much, ma'am, and thank you, sir.
Welcome.
Thank you, Lakshmi. Yeah, Jaskaran, you can.
I think that he may not be able to speak. That's why he is messaging.
Jaskaran, if possible, you can interact directly. Someone asked about the links of tomorrow's class. Jaskaran, it's okay. Someone asked about the classes of tomorrow. Tomorrow we have in the morning, we have a session on selected problems from TIFR graduate school exams by Arun Kumar, a research scholar from Kerala School of Mathematics, Calicut. And also in the evening, we have another session on functions of one real variable by Vishnu Ravindran. He is a research student at Karlstad University, Sweden, and he completed his MSc from TIF. Okay, others, if you have anything to ask, now you can do.
Excuse me, sir. Sir, in which groups do you share that link?
See, we are having math aspirants groups, and also we have a Telegram group, Math Ecstasy. If you join in any of that, the links will be available there.
So, can you please share that link to join the group?
See, where did you get the link of today's class? In that, I think my number will be there. You can WhatsApp it to that number.
Okay, sir.
Okay, others. Okay, what actually Jaskaran commented in the message, I didn't notice it. Bhavya, did you see that?
Yes. I have read the complete message.
Is there any question or anything?
Yes, you asked a question also. Can you recommend a book to read after Galleon? Yes, I can obviously recommend a group to read. You have understood the Galleon completely. If you have understood the Galleon completely and with you have solved its questions also, then it's more than sufficient. But if you have difficulty in understanding the steps or you want more examples in a book, there is a book by V.K. Khanna, S.K. Bhamri, Abstract Algebra. It is a good book. It has many examples and all the topics are covered. It has exercises also, which are good. Moreover, there is also Damit and Foote. If you have understood Galleon completely and solved all the questions, then refer to Damit and Foote because it's a bit higher standard book. Abstract Algebra, Damit and Foote.
Yeah, there are many classical books like Michael Artin and also, of course, the great one by Ian Herstein, the classical one, Topics in Algebra.
Yes, that is also there.
Good reference. Yeah. Okay, others, if any of you have something to comment. Yeah,
hello, miss. I'm Hiba Mohammed from Kerala. It was a nice session, and you have discussed many different questions, and you have given a solution. And thank you, miss, for arranging this class.
Thank you, Hiba. Any others?
I think now we should conclude our session.
Yeah. Okay, so let us wind up here. Once again, thank you, Bhavya, for this evening.
I should thank you to give me such an opportunity to interact with so many students.
and increase my experience.
And I hope that you will join again with us with some more problems. Yeah, you can include a little bit lighter ones too, so that they can enjoy it more better.
I didn't have the background of what they have been studying. I thought they are doing for JAM, so they must have studied these topics because it is previous year JAM only I have taken the questions from.
See, all these COVID issues turned the situations into different levels. The classes, everything are not in the right
Yes,
track.
sir.
So many
Moreover, syllabus is also different from North India.
yeah, that may be
We have
this.
studied
But anyway,
up to
they have to learn all these things. So that is why no problem for in your selection. But at the first time, they have got some difficulty in understanding the things, I think.
yeah,
So
they must.
you can, next time you can include a little bit easier ones too, so that
Yes.
they will be more enjoying and understand. Okay, I'm sure that this time also, but they have developed some kind of feeling, some fear. These many things are there, and like that. Okay,
Right, sir.
it's okay. Anyway, thank you, Bhavya. So, wish you all the very best for your studies.
Thank you, sir.
Let us hope that our group and our other classes will be useful for you as well.
Yes, sir, they are.